All right. So, thank you. So today I will talk about something very much related to what I talked about last time. So we recognize many pieces of the story I talked last time. But the main motivation, the main goal will be slightly different. The main goal, so last time the main goal was to say something answering a question in the physics literature. Here the main goal will be to state a result which is about moduli spaces in algebraic geometry. So it's about KSBA moduli spaces of Pierrick BOUSSEAU surfaces. And the main result I will talk about will be a statement which could be understandable by a birational geometer which knows nothing about a mirror symmetry, but some of the proof will use in an essential way mirror symmetry. And even why the result should be true is kind of motivated by a mirror symmetry. And so from a mirror symmetry point of view, the kind of thing we'll talk about today is a kind of the global moduli space of complex structures. So during the tutorial, Conance recalled that if you have some symplectic side, let's say some A side and some B side, then there should be some kind of space of symplectic structure in some kind of space, and there should be some kind of space of maybe complex structure, and these two spaces should somehow match. And the kind of thing we'll care about is try to say something about some global moduli space on the B side, which is something that complex or algebraic geometers care about. And somehow to do that, we'll do some mirror symmetry, get some information from the A side. So it's a bit opposite to the one of the early reasons to care about mirror symmetry is maybe to say the A side, maybe you're counting curve, it's a difficult question, and the B side is easier, you calculate periods where it's easy, so you get some information on the A side from B side. But what we'll do today, it will really go the other way around. At the end of the day, we'll prove something on the B side and really use the A side and do some curve counting, some log Gromov-Witten theory to ultimately prove a result in complex or algebraic geometry. So before going there, I want to say a few words about some class of moduli spaces, these KSBA moduli spaces, which are of general interest in algebraic geometry without reference to a mirror symmetry. And you can think of these moduli spaces as higher dimensional generalizations of the Deligne-Mumford moduli space of stable curves. So let me recall that you have the moduli space MGN bar. Moduli space is of n-pointed GSG stable curves. And so what these moduli spaces parameterize a stable curve, which consists of a curve with n mark points. And there is some condition on the singularities, so you want the curve C to be at most nodal. And you want the points Pi to be smooth points and distinct. And this curve C as a GSG, arithmetic GSG. So there's a condition on the singularities, and there is a stability condition, which is usually stated by saying that the automorphism of the curve preserving the mark points should be finite. But this condition can be rephrased in an alternative way as saying that if you look at the canonical divisor of the curve, and if you add the divisor consisting of the mark point, then this divisor should be ample. So in other words, this curve with its mark points should be of general type, in the sense that the log canonical divisor, so the canonical divisor plus the divisor of points should be ample. So it's a general type condition. And it's known that these moduli spaces are extremely nice. So these moduli spaces, they are a proper DM stack. And so the whole point of this notion is that you introduce enough singular objects to get something proper, something compact, but you don't introduce too much to get something too wild. In particular, this thing is like separated as a stack. So roughly, if you have a family of curves like that, a one-parameter family, there will be essentially a unique limit among this curve with mark points. And the KSBM moduli spaces, which have been introduced by Kolar, Schipper-Baran, and Alexis, starting in the 80s, is about moduli spaces which parameterize not just curves, but higher dimensional varieties. And you see that even for curves, we don't really parameterize curves, but we parameterize curve with mark points. It's the most natural setup. And so in higher dimension, what you consider will be so-called stable pairs. Y, comma B, where Y is a projective variety. Now of some dimension D, and B is some. So here we have points. In higher dimension, we want to replace points by divisors. And this thing will be a Q divisor. So meaning it's a formal linear combination, some of the AI, BI, where the BI are like reduced divisors, reduced Vel divisors. And we allow the coefficients AI to be rational numbers between 0 and 1. Okay, so you have a pair of a variety with a divisor. And as for the case of curves, you want to impose some condition on the singularities of the pair. And the technical condition is that you want this pair YB to be a so-called SLC, so semi-log canonical. So this thing is a technical condition on singularities coming from the minimal model program in birational geometry. In dimension 1, it reduces to this condition that the curve is at most nodal and that the points are smooth and distinct. And in higher dimension, it's a more complicated condition. In particular, you can have singularities which are worse than normal crossing or worse than toric. You can have things which are not log smooth in any sense, and this thing will be relevant for later when you try to run some mirror symmetry. Okay, so the first condition is this condition on the singularity. And the second condition is a kind of stability condition. And the right generalization is the second one, is to say that ky plus the divisor should be a Q Cartier, so a multiple of it should be Cartier, should correspond to a line bundle, and this line bundle should be ample. Okay. So you have this notion of stable pairs, a variety with a divisor with some condition on the singularity, and this kind of general type condition. And what KSBS is starting to prove in the 80s in dimension 2, and then it has been continued in the following 25, 30 years, is that these moduli spaces, if you fix the natural kind of numerical invariance analog to genus or number of mark points, you get some moduli spaces which are a proper TM stacks. And so by now there is a kind of fully complete theory of these moduli spaces in higher dimension. There's a textbook by Kolar which exposes a theory of these moduli spaces of varieties. So the main difference with the case of curves is that for the case of curves, this moduli space is actually smooth as a stack. It's like an orbifold. Whereas for higher dimensional varieties, these moduli spaces can be badly singular. They could have several irreducible components. They could be non-reduced. They could be arbitrarily singular. And in general, the kind of question you might ask is to describe some concrete irreducible components of this moduli space. In general, doing that in some concrete example is something not easy at all. So I will first explain a particular a situation for which it is known how to describe one of these moduli space, which involve toric geometry. And then the main point of the talk will be to say something about some non-toric varieties, these log-Calabi-Yau surfaces. So let me say something involving toric varieties. And here I will start using the same notations as yesterday. I will start with a YD, where Y is a projective toric variety. And I will denote by D the sum of the Di is a toric divisor, which is a union of toric divisors. And then on this projective toric variety, I will pick L, some ample line bundle. So we know from toric geometry that this data of an ample line bundle on a projective toric variety is the same thing as the data of some P, some lattice polytope. And then if I have an ample line bundle, if I pick a section of this line bundle, and if I look at the vanishing locus of this section, I will get some hypersurface, some divisor inside my toric variety. So I can look at what I will denote by C, some element in the linear system of the line bundle, it's some hypersurface in my toric variety. And I will look at pairs of the following form. So in this theory, I want to have a pair of a variety with a divisor, and I want to have ky plus b to be ample. So why do we care about this additional divisor? Why not just take a toric variety with a toric divisor, for example? So in this situation, because the divisor is always anti-canonical, you have ky plus d equals 0. So if you have a log-Calabi-Yau pair, it will never satisfy this condition, because the log-Calabi-Yau pair, ky plus d will be equal to 0, so it will never be ample. And so the general idea here is to try to get a moduli space which fits into this general theory by adding to ky plus d something ample to it. So if we pick an ample line bundle, we have an ample divisor. We can just add it to the toric boundary to get a pair satisfying this condition. So I will consider pairs of the form toric boundary plus C. But actually, I want to be really close to the log-Calabi-Yau situation. So I will put a coefficient here, which is epsilon, where epsilon is a very small positive number. In this situation, if I look at ky plus its divisor, so ky plus d0, I get epsilon times c. I get something very small but positive times something ample, so this thing is ample. So I can look at pairs of this form. So if I draw a picture, maybe here is my toric boundary of my toric variety, so this thing is D. And in addition, I have some C, some hypersurface in the linear system of this line bundle, something like that. And so I consider a pair which is Y, the variety, and the divisor is a union of this white toric boundary and this yellow hypersurface, ample hypersurface. And you might ask, when is such a pair a stable pair in this sense? So the stability condition is automatic because ky plus d plus epsilon c is ample, so this thing is fine. And you might ask, what about the singularity condition? What does it mean for such a picture, for such a pair to be semi-log canonical? And what you can show is that such a pair is semi-log canonical if and only if this hypersurface C avoids the zero-dimensional strata of D. So avoid the torus fixed points as in this picture. So I can take any element in the linear system of L. It can be very singular. as long as it does not pass through the zero-dimensional strata of D, as on the picture, this pair will be a semi-log canonical pair if epsilon is small enough, which is where this condition is used. So we can form a moduli space, which is simply the moduli space of all such a pair. So essentially all such picture. So here YD is fixed and simply this hypersurface move in the linear system. And as long as the hypersurface avoids the zero-dimensional strata, it is a stable pair. But of course, sometimes this hypersurface will go through a zero-dimensional strata. So this thing will not be stable, but the general theory tells me that I can take the limit inside the moduli space of all possible stable pairs. So I will define MYDL as being the closure of this locus inside this abstract moduli space of all possible stable pairs.
So you're assuming that Y is toric.
Yeah, so here I'm start here YD is a toric pair. Yeah, Y is toric.
In that component, we can move away from toric, right?
So here, yeah, first, yeah, I look at pairs of this form, and so actually a toric variety as a pair does not have any non-trivial deformation, like locally, as long as it stays irreducible, like it is as a pair somehow. And so here YD is always toric. I'm restricting to pair of this form, where YD is toric and I have C in the linear system. I look to the locus.
Information of pair, then you can become non-toric.
And I fix, so I don't allow the divisor to smooth out in any way. So I want to fix, like D is kind of fixed, deformation of pair with D being fixed. With D being fixed, yes.
Abstracted as a normal cosine divisor.
Yes, that's right, absolutely. So of course in P2 I could smooth a corner and then it become a non-toric pair.
Right.
So, but yeah, I don't want that. I want to fix D as an abstract variety. So clearly, so in the middle I get that, and then I take the closure, I get something in the boundary, and maybe it's not fully clear what I will get. But as we'll see in 1 minute, what we'll get will be some union of toric varieties. So actually, so the theorem of Valéry Alexeev around 20 years ago is that if you look at this moduli space, more technically, if you look at its normalization, of this moduli space is a projective toric variety So maybe in general it's unclear what this kind of closure inside the moduli space of all stable pairs look like, but the claim is that this variety is actually a toric variety. And if it's a toric variety, it should have a fan. And its fan is a non-object. And maybe familiar to some practitioner of mirror symmetry, with fan given by the secondary fan of the polytope P corresponding to my toric variety with my on-pole divisor, where secondary fan is some object defined by Gelfand, Kapranov, Zelevinsky. And so we'll not review the full definition.
This is independent of L.
So this thing depends on L, because the polytope depends on L. The P is like the momentum polytope for L, yeah. So yeah, so it depends on L, yeah. And so this is a secondary fan. So it's a fan which live in some vector space of dimension equal to, so it's like the number of integral points inside your polytope minus the dimension of y minus 1. So if your polytope contains a lot of integral points, this thing is a very high dimensional space. And its maximal cones correspond to regular triangulations of P. So this secondary fan is just something combinatorial. It's a fan which encodes the combinatorics of polyhedral decomposition of P. Let me give an example. If P is a two-dimensional lattice polygon, then, so in this example, I have 1, 2, 3, 4, 5 integral points. This thing is two-dimensional, so I remove 2, I get 3, and I remove 1, I will get 2. So the secondary fan will be two-dimensional. And you can check that the secondary fan in this case will be this fan. And the various maximal cones will correspond to various ways to triangulate this polygon. So here is one way to triangulate it, which is that way. And there's another way which is that way, and another way which is that way. So the triangle do not have, like, it's okay to have vertices on the side of the triangle. It's this definition of triangulation. So here are the kind of three ways to decompose this polytope into triangles. And they correspond to the three cones of this fan. And so there is a general definition of such a fan, and you always get a complete fan, which then define you a toric variety. So I get some corresponding toric variety, which in this case will be P2, because this thing is a fan of P2. So I get a toric variety like that. And the various torus fixed points correspond to this kind of triangulations. And the kind of intermediate strata correspond to like various intermediate polyhedral decomposition.
Sorry, is it? Did you mean to put a vertical for one of these?
Yeah, that's right. You are perfectly right. Thank you for pointing out. As they will be the same. So yeah, one of them is horizontal, one of them is vertical. Yeah, thank you for pointing out. And they're the same because they differ by rotation of pi over 2, pi over 2, which is 0. Okay. So the claim is that in this example, this moduli space of pairs somehow looks like that. And so really, so what happens is this moduli space. So if I look at the point inside, so we know what we parameterize. We parameterize the toric variety with polytope look like that. So the variety itself really looks like that. It has the toric boundary has 4 irreducible components. And parameterize, maybe I should not have done it in yellow, maybe in white. And there is an extra curve C, which is live in the linear system of L. So it's a curve which looks like that. And you can check it at genus 1 because there is one integral point here. So I have a curve of genus 1 like that. And then what happens on the boundary, so what happens here, for example, the claim will be that this picture of the triangulation will give you a picture of how our toric surface with this divisor degenerate. The fact the polytope breaks into 3 triangles will mean that our toric variety will break into, in this case, 4 copies of P2s. And correspondingly, this curve will degenerate into like curve in the linear system corresponding to these triangles. And these triangles correspond to the momentum polytope of P2 with O of 1 because it has size 1. So it's degenerate to union of lines.
So when you are moving at different point in the interior, it just corresponds to the same, or about just C is changing?
Yeah, that's why only C is changing in this story. That's why the toric variety is fixed and C is changing. And here similarly. So here the thing will only break into 2 pieces. And here it breaks into the 2 other pieces.
And so I guess going to the boundary is really you're like approaching one of the fixed points, torus fixed points.
Yes.
And then KSBA tells you to like break.
Yeah, that's right, exactly. So here there is some kind of abstract definitions of KSBA moduli space saying, so there is some very general theory which guarantee when you go to the limit, like this curve try to go through a fixed point, through a torus fixed point, which is forbidden. And the general theory will tell us there will be some limit, actually some unique limit, which will be a stable pair. And actually in this toric situation, what happens is can be described purely torically. Just a toric variety breaks into a union of toric varieties. And Sorry?
To the edge.
Ah, yeah, that's right. Then to the edge, one is to think, but it's like some intermediate. It's some intermediate situation. Actually, I think, yeah, what we need to think. I'm pretty, yeah. I think what really happens, I'm not 100% sure, but I think the thing does not break. But okay. Yeah, there is this subtle point that in this picture there is some interior, which is the torus in this toric variety. And here there is something which looks like the interior, which is a place where the variety is irreducible. But these two things do not coincide in general. So over C star square, you are always irreducible. But there can be places outside C star square which are actually still irreducible.
I mean, this is before compactification.
Yes, that's right. Before compactification. Yes, that's right.
So you say that the compactification only at 3 points?
Yeah, I think in this example it's only at the 3 points, yes.
If you follow that line, is there something like interesting that? Sorry, is the curve like very special, or on the like boundary line? Is it like satisfies some properties?
Yeah, I think what really the reason why this curve is in the boundary, it has some kind of extra automorphism. There's some kind of extra symmetries. Yes.
There should, like, if you follow the definition of GKs, that's at the same boundary, I think there are no interior integral points. Like in the definition of GKs,
yes.
The data of triangulation is the data of the decomposition together with lattice points. And I think on the boundary you have these triangulations without interior points.
Yeah, that's right. There is this. Yeah, there is some kind of refined notion of.
So the definition of GK is a bit subtle. It's not really just decomposition, but the decomposition together with the data of points. And I think probably you have more genus model or something. But this
Yeah, that's why we might need to double check what really happens. But I think what I said is probably. But yeah, indeed, the notion of triangulation, one needs to be careful is the correct definition. Okay. So this thing is just a result in algebraic geometry of this module space. You ask what happens at the boundary, and if you consider something toric, you have this toric variety breaking, which are captured by these subdivisions of the polytope. Now the question is, first question, which should be relevant for us, is what does this thing has to do with a mirror symmetry? So the claim is that this picture we obtained here is actually a picture of a module space of complex structure.
So in the case where y is p1, so
yes.
p is just 2 points, right?
Yes.
You only have 2 plus epsilon point. That's already stable? Semi-stable?
Yeah, that's right. Yeah. So maybe I should mention, so if you're in dimension 1, if you look at P1 with these 2 points, and if you take epsilon times a bunch of other points, these spaces have some names. They have the Lozef-Manin spaces, which are like alternative compactification of 0 curve with n mark points. It's like not the standard M0 n bar, which are not toric, which will correspond to taking all the weights to be 1. But if you take 2 weights being 1 and the other being epsilon very small, you get some toric varieties. Then there are some fan, I've forgotten which fan it is, but it's a fan which has a name. Yeah, maybe it's a permutahedron, the polytope dual to the fan you get. But yeah, you get something interesting. Like you get some kind of something toric birational to M0 n bar, for example. Yeah, this thing is called Lozef-Manin spaces. And this thing is already something interesting to think about if I want. So so what's the relation with a mirror symmetry? So here I have this YD, which is a log-Calabi-Yau pair, but I have this extra ample divisor. And so what I will do to connect it to mirror symmetry for Calabi-Yau is exactly the construction we discussed yesterday, which is what I denote by Z, which is this non-compact Calabi-Yau threefold, which is UV equal f of xy, where f is a Laurent polynomial with Newton polytope equal to P. So if you want F is a kind of equation. Okay, so actually this thing works in general in any dimension. If you're in dimension D, it's like just have more variables. F is the equation of this hypersurface restricted to the torus inside your toric variety. And this thing is like, so it's a non-compact Calabi-Yau. And because it's non-compact, I don't know how to really make sense of its moduli space of complex structure deformation in a fully precise sense. But certainly it's true that if these hypersurface vary, it's like varying the coefficient of F, and certainly this thing should be viewed as varying the complex structure on Z. And so I can think of this moduli space, this kind of compact moduli space, as some kind of compactification of some kind of moduli space of complex structure on this Calabi-Yau Z. So this moduli space is some kind of compactified B-model parameter space. Okay, so this is toric variety corresponding to the secondary fan is some kind of B-model parameter space. And in particular, these various fixed points, so actually the one on the top will be a large complex structure degeneration for CZ. So if I draw this picture here, here will be some kind of large complex structure limit point for CZ, for this higher dimensional non-compact Calabi-Yau, which is built from this curve restricted to the open torus.
But are there other deformation parameters for this?
So, yeah, so again, because it's non-compact, one needs to be careful. So I will take as definition as like varying the complex structure of such Calabi-Yau as being just varying F, the coefficient of F. Yeah. And in this example, the other, yeah. And so in this example, there's only one large complex structure limit, but in more complicated examples, there could be several large complex structure limit points which correspond to the various triangulation into like very small triangles of size 1. So this thing is the first remark, which is that these moduli spaces which come from this just moduli space question, first it has a meaning in mirror symmetry. It's some kind of B-model moduli space. And here, related to something that Michel mentioned, so here over this B-model moduli space, there is some kind of universal family which is extended over the boundary. Because by construction, this thing is a moduli space. Over every point, I have some YD. I have this kind of degenerate version of this toric variety, and so I will have some kind of degenerate version of this Z. So it's one of the maybe rare example where there is some kind of B-model moduli space which is kind of compactified, and it's really compactified in a modular way. Okay. But this thing is a B-model story, so this picture should have an A-model meaning. Like on the mirror side, this picture and this fan should have a meaning on the mirror. And this thing is known in toric mirror symmetry. So what is a mirror side? So I will use the same notation I used yesterday. If I have a polytope P, I can consider X bar as being the toric variety with fan the cone of a P. It will be this singular affine toric variety with a canonical singularity. And the claim will be that these various polyhedral decomposition of P define partial Crepont resolutions of X. So I get of X bar. So I get partial Crepont resolutions corresponding to these various cones in the JKZ fan. And in this example, we could see what happened in this example. So as I was describing yesterday, this thing will always be fibered over some C, and there will be a fiber over 0, whose picture you get by taking the kind of web of branes dual to this picture, which look like that. And you should interpret that as being polytopes of the components of X0. And here you see a square, which is a polytope of P1 times P1. And actually, the corresponding Calabi-Yau threefold E is like the total space of P1 times P1. total space of the canonical line bundle over P1 times P1. It's like local P1 times P1. And then what is the meaning of this cone? This cone is an F cone of this X over X bar. So it's the algebra geometric version of the Kähler cone of this X. It's just it's like the closure of the ample divisors on X. And the other ones are related to this one by some birational transformations. This thing will be dual to this thing. So here there will be one P1 times C1 will contract along some vertical P1. And then it will be the other ones. And actually, if you look precisely what is the result of this contraction, here there will be some orbifold singularities in this threefold. So it's always true that the kind of maximal cones correspond to some kind of smooth, in the orbifold sense, Kähler-BOUSSEAU. So this thing is like some X prime. This thing is like some X double prime. And if you define correctly the Neff cone of an orbifold, you will get this kind of cone. So in some purely algebra geometric language, there is a story involving bogus cones that I will suppress if you just believe that orbifold things behave as nice things. There should be a correct definition of Neff cone for the orbifold thing which produce this picture. So the output is that this fan, this secondary fan, from the mirror point of view, is something which is dictated by the birational geometry of the Crépin resolution of this X bar. It's a kind of the union of the Neff cone of all possible Crépin resolution of this X bar. And again, it's something you might expect from the general mirror symmetry because the toric variety corresponding to this Neff cone is some kind of model for some complexified Kähler moduli space of this X, which would give you some local picture here. So here this thing is a toric variety. Here there is some affine chart around this point. And the claim that this affine chart is really identified with some kind of complexified Kähler moduli space of this X, which is defined as the affine toric variety with fans this Neff cone.
So this is a flop?
Sorry?
This is a flop?
So this thing is not, this thing is like a divisorial contraction. The divisor is fully contracted. So it's not a flop, it's like divisorial contraction.
But that contraction usually just go to the boundary.
Oh yeah, oh, you mean flop from here to here, maybe?
For example,
Yeah, from here to here, this thing is more like a flop. Yeah.
that one is not.
But this one is not. It's like a divisorial contraction, like the divisor. So it's pretty true that if you work in some kind of orbifold world, maybe everything should be called flop. But in classical algebraic geometry, this thing will be called divisorial contraction because something is contracted. Like a divisor disappears. So here it changes in codimension 1. Usually a flop only changes thing is codimension 2.
But when the contraction is only when you hit the boundary, but then you start to move the orbifold.
Oh yeah, so it's kind of the point. It's related to this orbifold thing. When you go from there to there, actually nothing happens. The things stay orbifold. Like you get contracted and become orbifold, and actually the geometry does not change here. So it's like in mirror symmetry, it's kind of, it's one of, maybe it's like hidden parameter you don't really see in,
But that can be seen in the complex side.
Yeah, that's on the complex side, it can definitely be seen. Like there is a full,
So that corresponds to just that point.
Yeah, that's just that point. Yeah, that's.
I think this is confusing as there are focus cones using the secondary cone is really just.
Yeah, that's one way to that. This cone does not really exist. The Neff cone of this geometry, in a strict algebraic sense, is only this array. And then there is a way out from the Neff cone to cook up something called a bogus cone by Shankill, which is you add to this Neff cone of this geometry the array spanned by the divisor you contracted, which disappeared. And you add this array, and then you produce this cone.
How do you add that way?
So this array is a array spanned by the class of the divisor you contracted when you go from here. And you can check if you do the calculations, this divisor of this P1 times P1 live here in this picture, in this space of divisors. And so you should add this ray. And it's a general theorem that if you always do that, at the end of the day, you get a complete fan, which match exactly the secondary fan, yeah, which is a secondary fan. It is purely toric story. Okay. So what I just reviewed is some kind of part of more or less standard toric mirror symmetry, but which is phrased in a way which is kind of almost perfect. Like on the B side, you have a compact moduli space. And it's actually a toric variety. It has a fan. And this fan has a clear interpretation on the mirror side as being some union of Neff cones corresponding to the various Crepont resolutions of some kind of singular mirror. So here's what this picture is saying is that in this particular situation of Crepont resolution of X bar, there is some clear like global A model moduli space. For each resolution, there is some kind of local thing related to these Neff cones, but these Neff cones all fit together in kind of nice global picture. Yes?
Just something, if I may. I feel like you're always rushing too much. Maybe I'm happy to give you one of my lectures so you can just do the toric thing now and do the non-toric thing in another lecture. I'll be very happy.
Yeah, we'll see. So yeah, we just continue without rushing, and I will stop on time, and then we'll figure out. Probably we'll continue at some other point. We'll figure out. Yeah, thank you.
I'll be very happy if you do that.
We'll see. Yeah.
I think this thing got equipped with like electric, so you get some shock if you over time. So it's my fault.
Yeah. Okay, so actually it's essentially everything I wanted to say about the toric situation. But now we'll start saying something about the non-toric situation. It might take some time, so I might still need some time afterwards.
And then to answer Michel's question, I do believe what's happening on the slides is the curve of genus 1 is, if you have a vertex in the middle, I think breaks into two curves with multiplicity intersection 2 on the boundary, if you have a vertex. Like, and the other, if you omit the vertex, I think it just amounts to having two curves intersecting 1, 1.
I see. Let me check.
So I think this is adding versus subtracting.
It's very likely. So probably what I said here is not.
I think you said everything fine. So yeah, on the edge there's this thing where you just don't have the vertex. You have a dotted vertex.
Yes.
And I think it amounts to breaking the curve not with multiplicity 2 but 2 points 1, 1 or something.
Yeah, we can check later.
Okay.
Because I'm not really sure. Yeah.
You don't believe.
I know, like so here the surface breaking, is it breaking into two pieces?
Yeah, the surface
Okay.
breaks into two pieces.
And the curve?
The curve also breaks into two pieces, but on that side it intersects with multiplicity 2 on the edge. Because if you,
Yeah, but this thing cannot degenerate to something where things are not of multiplicity 2. It could be the other way around, maybe. The other way around will be more likely, maybe.
I think it's the other way around, you're right.
Maybe. And then maybe here it will be. But then how could it be genus 1? Yeah, maybe it's fine. Okay, something like that, maybe. Okay, so this thing was essentially a toric story. And now you can try to modify it. Instead of starting with YD, a toric variety with a toric boundary, you might try to replace YD by any log Calabi-Yau pair. So now some non-toric story. So you might want to replace YD, which was a toric pair. So what we remember from the toric condition is that the ky plus d is equal to 0. So d is anti-canonical. This thing is a log Calabi-Yau pair. And what we also want to remember from the toric case is something Julia mentioned in a talk. We want this pair to be maximal, meaning we want D to have a zero-dimensional stratum. So D contains a zero-dimensional. So in toric geometry, the zero-dimensional stratum, as reviewed in the tutorial session, it's a place where one of the S1 to the n torus in the toric variety shrink to a point. And conversely, you might think that if there is a zero-dimensional strata, then maybe locally there should be some kind of S1 to the n fibration on the complement. And so you want this kind of condition. So this condition should guarantee, hopefully should guarantee that there is some kind of Lagrangian torus fibration in the complement. But because no longer toric, possibly with singularities in the middle. Okay, so we want to consider this kind of maximal log Calabi-Yau pairs. And as before, we add the ample line bundle. So here I will also fix L some ample line bundle. And we'll define exactly the same moduli space here than here. We will again consider divisors in the linear system of this ample line bundle. And again, we can check that as long as this hypersurface avoids the zero-dimensional strata of D, this thing will be a stable pair in the sense of KSBA theory. So this pair y d plus epsilon c for epsilon small enough will be stable if C avoids the zero-dimensional strata of D. And as before, we can define some moduli space, which is some kind of closure in the moduli space of all the pairs of this form. So the number M ideal. So I look at all of these pairs satisfying this condition. And I take some kind of closure. And by the general theory, this thing is like a proper moduli space. And so here there is some difference with the toric situation, which is related to Conan's question. There is a claim that this pair, if I fix D, then actually there is no deformation of the pair on this open part. But now in this marginal log Calabi-Yau situation, even if I fix D, then the complex moduli of Y could vary. So for example, one way to produce such a pair which are non-toric, as was described in Julia's talk, is I can start with something toric. For example, there is this P2. And I can take a point on the toric boundary, which is not one of the torus fixed points, and take the blob of this point. And I take for D the strict transform of the toric boundary. And I can blow up many points. For example, I can blow up all these points together. So this thing is my YD. And now this Y clearly has some complex moduli because I can move the position of these points I blow up. So here, so before only the curve C was, or like the hypersurface C was moving in the interior of the moduli space. Here, both the hypersurface and possibly the complex structure of Y are moving. But apart from that, it's a moduli space which has almost exactly the same definition as the toric situation. In the toric situation, where this result of Valéry Alexeev saying that the moduli space is something toric. And this result reviewed is maybe not so surprising, because if you start with something toric, getting a moduli space which is toric is maybe not really surprising, because you start with some combinatorial data, and some of the output is just made of this combinatorial data. But there is a general conjecture due to I Can Kill You. Which predicts that if you start with any maximal log Calabi-Yau, then this moduli space will still be toric up to a finite, so up to some technical condition, which is like a finite map. So the claim is that there exists T, some projective toric variety, such that like T has a finite surjective map to this moduli space. So this moduli space is like extremely close from being toric. If you forget this technical condition, it's roughly saying this moduli space should be toric. And our theorem with Valérie and Filia is that this conjecture is true in dimension 2. Conjecture true in dimension 2. So in dimension 1, there is nothing to prove, because if you think what are the maximal log Calabi-Yau pair, actually here I forgot something. I wanted to say D is reduced in my definition of log Calabi-Yau. And so in dimension 1, this thing is only possible if Y is P1 and D is 2 points, so which is a toric situation. So in dimension 1, every such pairs are toric, so they are covered by the toric story. But starting in dimension 2, if you do this kind of constructions, you product like infinitely interesting non-toric log Calabi-Yau pairs. And so for all of them, there is something very non-trivial happening, and what you prove that is true for all possible two-dimensional log Calabi-Yau pairs.
But Y is not rational. Why would you expect that?
So good point. So Y does okay. So it will something which will help us in dimension 2, which is in dimension 2 Y will be automatic, will be rational. It will be, it's always birational to something toric, so it will be rational. And somehow we make technically use of that in our proof. But starting in dimension 3, there are indeed maximal log Calabi-Yau pairs where Y is possibly non-rational. But still, the general philosophy of the conjecture that I will review in the dimension 2 situation still should hold and should still predict that you get something toric. So it's fair to say that there is actually not much evidence higher dimension 3 that is really the case. Like I guess nobody has worked out an example of a non-rational 3-dimensional log Calabi-Yau and to check this. Yeah. But okay, I will explain where this toric comes from. It will be kind of the point. And we see that actually the general reasoning should hold. It does not really rely on Y. And really the reasoning will be mere symmetry. Like if you think in terms of YD, it does not really make sense because you get something toric out of YD, and YD is maybe not rational. But this toric structure will come from the mirror, really. And so.
But the conjecture is assuming that D has a 0-dimensional.
Yeah, that's right. So definitely, if D does not have a 0-dimensional strata, certainly the statement is not true. Like because if we take like a P2 with a smooth elliptic curve, and then if you just move, you will see something like the moduli space of elliptic curves, which does not have a natural kind of toric description. Sorry?
Up to that.
Yeah, so there should be some kind of statement saying that up to that, something like that should be true, but it has not been worked out. It's actually something we are thinking about, but it's not.
For P2E? For
like for this kind of
yeah, but there's no maximum. I guess you put a non-max out there.
yeah, like
something similar should hold.
I mean, so certainly the KSB moduli space is well defined, and this thing will not be true, and you might ask what is the correct thing which should be true.
But I think a crucial point, even in the toric case, maybe we can illustrate the reason why this holds is the existence of a basis, nice monomial basis, for the sections of an ample line model on line. Like the reason why it holds in local Calabi-Yau is related to the existence of theta functions.
Yeah, so
Maybe we can tell why.
yeah, so I'll definitely mention that. Maybe not now because I have 5 minutes.
In
But definitely I will mention it next time, if not like today. Yeah.
In general, full generalities, do we have mirror symmetry for log Calabi-Yau in all cases?
So it's actually part of the point that this thing is motivated by mirror symmetry, but the whole point will be what is mirror symmetry? And so it is something I need to explain. And in dimension 2, the point will be that we can't fully realize mirror symmetry for all possible log Calabi-Yau surfaces. And yeah, so it's one of the, yeah. So I will only give the kind of rough picture of how this thing will happen. And then I will stop because I only have 5 minutes, and then I will continue either later in my talk or in William's talk. So the kind of general strategy, or like, so something should be a toric, so there should be a fan coming from somewhere. And from this kind of moduli space of B model point of view, it's unclear what this fan is. So in the toric situation, you could understand how toric variety breaks combinatorially, and you see a fan. But for a random log Calabi-Yau, you don't have an a priori understanding of degeneration of this log Calabi-Yau, so you don't know how to cook up a fan. But in the toric case, we learned that this fan has a kind of mirror interpretation, as a kind of union of Neff cones, of Crepont resolutions, of some mirror geometry. So the strategy is starting from our pair YDL, we will construct some X bar. So starting from null, and we say this thing is in dimension 2. We'll construct some X bar, some canonical threefold singularity. And then we can study Crepont resolutions of these canonical threefold singularities. And actually, I already explained how to do that last time in this physics story, starting from this brainwave. I sketched how to get that. So this thing is what we call the semi-stable mirror construction. So here it's already non-trivial. It's indeed related to the question, do we know how to do mirror symmetry? So here the claim is that in dimension 2, starting from this data, I know how to produce this geometry. And then there is something very general, which is where the fan comes from, which is a very general fact in birational geometry, which is Crepont resolutions of a canonical threefold singularity always form a Morey dream space.
So this perspective, you're figuring y is A side and x is B side?
So this thing will be the B side,
This is B side.
and
B
this
side to the A side.
thing will be the A side at the end of the day. But somehow, usually, to construct the mirror is either to start on A, B.
Yeah.
So it will be so we kind of do both. So it will be kind of the key point of the story to do mirror symmetry both ways. So this thing is the first way, and for the first way, it's better to think of that as A and this thing as B. But then when you have this geometry, you think about it as A. And then this Morey dream space condition will guarantee that if you look at this union of Neff cones of all possible Crepont resolutions, then this thing will give you a complete fan.
So this is always the case?
Yeah, that's right. So this thing is a very general result in birational geometry. In any dimension, it follows from this BCHM result on the minimal model program of Bierka, Caccini, Econ, McCannon. There is a very general statement that in any dimension, if you have a canonical singularity, if you look at all possible Crepont resolutions, there will be a fan. So this thing is really the reason why a fan should appear. And this thing should be only a property of this mirror being of this shape. So the mirror is kind of a canonical threefold singularity, and all possible Crepont resolutions, and there is a fan, guaranteed by general birational geometry.
If you're not in 2 dimensions, when can you get a canonical singularity?
Yeah, so I guess the expectation is that you should always get the geometry in any dimension. But the question is, how do you get it? How do you do for this construction? So.
We can always get the geometry, but in dimension 2 only we can prove that X is really smooth, and even dimension 3 we cannot prove the smoothness, I think.
Yeah, this thing is kind of an extra technicality. I think in general we cannot even construct that.
Even if we can construct
But yeah, it's kind of a point that even if we could construct it, the canonical threefold singularity does not always have smooth Crepont resolutions. There could be extra singularities. Which,
now we cannot
But
go
if you know
back.
the first step, you don't know.
yeah, that's why we don't know the second step anyway. Because the second step will be to run intrinsic mirror symmetry. So because we have a candidate fan, so we have a candidate toric variety, but to show that it is a moduli space, we need to produce family over this moduli space. So we need to run intrinsic mirror symmetry. And so to do that, we really use intrinsic mirror symmetry, meaning we'll really do some log Gromov-Witten theory of this geometry which require X to be smooth, which is like a technical thing which in higher dimension will be another reason why something might fail. Okay, so it's a general point. We want to prove something on the B side. Then we'll construct the mirror, which require going from A to B. Then we'll switch B to A, and then do mirror symmetry back. And it's one of the maybe rare examples. So of course, it's expected from the very beginning that mirror symmetry should be an involution in the appropriate sense. But if you think to construction like intrinsic mirror symmetry, it's not clear at all. It's very not obvious, and actually even to make sense of it is not clear. And so in this story, it will be one example where it's essential to understand mirror symmetry back and forth. And so next time I will say much more about this picture. Yeah, thank you.
Well, this seems to be a workshop on IMS. In IMS.
Yes, absolutely. So I have a question. If you did instead of, so you want to run intrinsic mirror symmetry on X, is that correct? Or
Yeah, so here it's like the degeneration situation. So like X viewed as a one parameter family over some one-dimensional base. Yeah.
oh, fantastic. And then that means you chosen a resolution, right?
Yeah, that's right.
And then you want to.
Yeah, that's right. So here actually it's much more than intrinsic mirror symmetry. Usually intrinsic mirror symmetry will give you something local around some large complex structural limit, but here we're on some global moduli space. So we need to run intrinsic mirror symmetry for each of these resolutions, and then we need to argue, first of all, they are just not just formal, but they really extend in algebraic families, and then they glue together. So there will be some non-trivial result if you take two different resolutions. The log Gromov-Witten theory are compatible enough such that the corresponding mirror family will glue to produce this kind of global picture of the moduli space, and not just some local picture around some large complex structural limit point.
Fantastic. And then my second question then, if you look at a fiber, like I did at the end of my talk, and then can you like reproduce IMS for that fiber, or not? Or is that like do you see the question? Like, can you like?
Yeah, I don't, because this fiber is kind of non-compact actually. So,
Right.
so I don't really do something relatively to compactification. So it's a bit of an orthogonal direction. I think.
Absolutely. And then maybe my third question. So in this picture, you really see that birational transformation corresponds to deformation, right?
Yeah, that's right.
And so that's a question to, so how general is that statement in mirror symmetry? Like, is it the case that, I don't know, Crepin transformations correspond to deformations? Is that like a general statement?
Yeah, so I don't know how general, I mean, I think like philosophically it should be true in general. And but it's an essential point of the proof to make it work in all details, because to get this very picture, we get to have a full picture of this moduli space. How do we go from there to there to there to there, which on this mirror side correspond to all possible, all these birational transformations. And I really need to identify what this birational transformation corresponds to on the mirror side. To actually and this thing is essential to prove properties of the mirror. And I might say a little more about that next time too.
That's really cool.